Okay, let me show you the contents of this video tutorial which I'm going to cover. First, I will talk about what is the Wavelet Packet Transform, a very brief intro. Then I will talk about the objective and the noise model. And then I will talk about the Wavelet Packet based denoising scheme. Then we will see that how one can estimate the noise variance and finding the universal threshold value that will be used for denoising. Then we will talk about the thresholding methods, and after that I will explain some MATLAB functions that will be used for wavelet packet decomposition and the wavelet packet based denoising. Then I will explain about the MATLAB code for denoising the one-dimensional signals. So I will cover some artificial signals as well as the real live audio signals, and then I will talk about the MATLAB code for denoising the two-dimensional signals and images. So let's go ahead, but before going ahead, I also recommend you to watch following my two videos. The first one is about the introduction to the wavelet theory and its applications. So here all the basics of the wavelet transform are covered, and the link is given in the description. And the second video is about the wavelet packet transform of signals and images. So this video is actually the base video to understand this current video. So if you go through this video, you will have the better exposure about the current video, and all the theoretical aspects of wavelet packet transform are covered in this video. So this link is given in the description. One can also watch these two videos which are about the denoising of 1D signals and the 2D signals using wavelet techniques. These two are about the wavelet techniques. So that techniques is very much similar what I'm going to talk in this current video, that is about the wavelet packets. So if you can watch these two videos, you will have again the better exposure about the denoising schemes. So now let me start the topic. So let's see first what is the wavelet packet transform. So the wavelet packet transform is actually the generalization of the orthogonal wavelet transform. So in the wavelet packets, the finer analysis is done by breaking up the the high frequency components into the corresponding approximation and the detail coefficients. And as we know that in wavelet transform, these detail coefficients are not split, only the approximation coefficients are split into the corresponding further approximation and detail spaces. So the concept of this wavelet packets was first introduced by the Kaufman, Mayer and Wickerhauser in the 1990s in order to mitigate the lack of the frequency resolution of the wavelet analysis. So let's see some applications. So the wavelet packet decomposition is very useful and has a number of applications. The very basic is the signal and image denoising, then signal and image compression, spectral analysis, object detection, signal and image classification. So in this video I'm highlighting this one, the denoising of signals and images. So now let's see what is our objective and what type of noise we have considered. So when a signal is transmitted over some distance, definitely it is contaminated by the noise. The term noise actually refers to the random signal which causes the undesired changes in the original signal. So here you can see that the simplest model for the acquisition of the noise is additive noise, so which has this form. So this is my original signal fk, which is added with the noise signal nk, and that's why I'm getting this contaminated signal f dash k. So in this tutorial, this noise nk, we have considered the white Gaussian noise with a zero mean value. There are different types of noises also, but this is very common which we have considered. So here our objective is to suppress this noise signal nk from the main signal, the noisy signal, to recover the denoised signal using the wavelet packet transform technique. And this is the wavelet packet transform based technique. So this is the overall block diagram. You can see that you have the noisy input signal, let's say f dash k. First, using the wavelet packet transform, it is decomposed into various coefficients. Now these coefficients are thresholded with some rules, and after the thresholding, all these coefficients are collected, and with the inverse packet transform we get our denoised signal. Here thresholding is important. So how the thresholding is done? Definitely we need a threshold value. So how to calculate this threshold value? Actually, there are various methods to find the threshold value. But here in this video I'm using only a single method, and which is most popular, that is the universal threshold method. And to calculate the threshold we need actually the noise estimation also. So we need to find the noise variance. Again, there are various methods to find the noise variance. In this tutorial I'm using the MAD method, that is the median absolute deviation, to find the noise variance sigma. So that I will show you in the next slide. So let me show you that how the noise variance is estimated and how we can find the corresponding threshold. So in this scheme, a single threshold value is used for thresholding all the wavelet packet detailed coefficients. So this threshold value lambda is calculated by the universal threshold method, that is also known as the square root log method, which was proposed by the Denoising and Silverman, and it is given by this equation. So you can find this lambda by sigma j square root 2 log nj, where nj is the length of the wavelet packet coefficients, detail coefficients, okay, at the level j, and the sigma j is the noise variance at that level. The value of this sigma j is calculated from the detail coefficients at level j using the median absolute deviation, that is known as the MAD. So sigma j is MAD upon 0.6745, and MAD is actually the median of all the wavelet packet coefficients at scale j or level j. And for present case, since we are taking only a single threshold for all the coefficients, we are finding the noise variance at scale 1, okay, and we are finding the lambda on the basis of the detail coefficients at the level 1. So that is the lambda 1 that will be used for thresholding all the coefficients. And now let's see what are the different thresholding methods. These two are very popular and very common. The first one is the hard thresholding, second is the soft thresholding. In the hard thresholding, you can easily see that within a range from minus lambda to plus lambda, all the coefficients are neglected, I mean they are simply zeroed out. And after the lambda, the remaining coefficients are unchanged, they are left unchanged. So we are not changing anything in the magnitude of these coefficients after plus minus lambda. And in the soft thresholding, you can see that we are again neglecting all the coefficients in the range from minus lambda to plus lambda. We are simply making them 0, but at the same time all the coefficients after lambda, they are also suppressed or is downscaled by some constant value. Okay, so this is not a 45-degree line originating from the center like this. Here all the coefficients both sides are downgraded by some constant value. So that is the soft thresholding. There are other methods also, so that I'm not taking into account in this current video. And now let's see how we can implement the wavelet packet decomposition using the MATLAB. So this is the function which we can use wavelet packet decomposition for one-dimensional signals. So let's see what are these parameters. So this T is actually the output decomposition wavelet packet tree, and the S is the input signal, N is the number of decomposition level, and W name is actually the name of the wavelet which you are using for the decomposition. E is actually the entropy type. It computes the entropy at each node of the tree, so that will be utilized in the denoising and compression stage. And P is the threshold parameter that is associated with the entropy parameter E. So P is not required for all E types. For example, the Shannon entropy or the log energy entropy, we do not need any P. So P is put simply 0. And for other types of entropy, we need the value of P. So for more details, you can refer MATLAB documentation. And this is the function WPDEC2 for two-dimensional signals if you are decomposing your images. So let's see what are these parameters. So T is again the wavelet packet output tree, I is your image, and the number of labels, decomposition labels, wavelet name, and ENP again are same. I mean your entropy criteria and the threshold parameter that is associated with this E. And now let's see how the denoising is done using the wavelet packet technique in MATLAB. So MATLAB has this inbuilt function, so that is WP den CMP. Actually this function has the capability to denoise as well as to compress the signal. So the same function can be used for both objectives, but here our objective is denoising, so we will use this function for denoising. So let's see what are these parameters. So first see the output parameters. So XD is your denoised signal or image. The same function can be used for both 1D and 2D. Okay. So what is WPTD? WPTD actually is a wavelet packet tree that is utilized for denoising. So if you know the theory of wavelet packets, then you might know that we have the two types of trees. I mean the full decomposition tree and the best tree, which is chosen on the basis of the entropy criterion. Okay. So if I choose a particular entropy criteria, ECRIT, that is the entropy criteria, then on the basis of that it can compute the best tree. Okay. And here F1 is actually the compression score, so it is useful only in the cases of compression, because I'm using denoising, so I don't have any use of it. And then F2, so that represents the L square energy recovery. So energy recovery is simply in the percentage, so that is the square, I mean the energy of all the wavelet packet coefficients of denoised signal divided by the energy of all the wavelet packet coefficients of original signal, I mean the noisy input signal. So that is simply the ratio of the energy. And for the input parameter, your T is a wavelet packet decomposition tree. So that tree can be obtained from the previous two functions which I have just explained in the previous two slides. And S or H, this is the simply string. You have to provide the two inputs, one either S for soft thresholding and H for hard thresholding. And as I said already, the ECRIT is actually the entropy criterion, and THR is a threshold value by which we will threshold the detailed coefficients at various levels, and key PEP has actually the two possible values, either 1 or 0. And now let's come to the MATLAB program. So here this is the MATLAB program for denoising the audio signals, or I mean the one-dimensional signals, audios or others. So first we have to load the noisy signal in the workspace. So first I'm using some MATLAB's inbuilt noisy signals. Okay, so these are some MATLAB inbuilt noisy signals like noise block, noise bump, heavy sign, noise stop. So you can use any one of these. So for example, this is uncommented, so when you run this, noise block will be used, while other are simply made comment, so they will not be executed. So you just uncomment one at a time to use the signal, any one out of these. And if you want to denoise your own signal, then simply uncomment this part of this code. Okay, so here it will ask you, once it will be executed, it will ask you select your input audio, and once the input audio is read, it will go to the variable X. And here I am just checking whether it's a stereo signal or a mono signal. If it is a stereo, then I am reading only a single track. And then if your signal is clean, then we can add some noise, a white Gaussian noise to this signal, so that you can see the denoising process. And if suppose your input signal is already noisy, okay, then there is no need to add the further white Gaussian noise. So simply disable it at that time if your input is already noisy. And now just finding the length of the signal and defining some parameters which are required for denoising. I'm using the Simlet 4 wavelet for denoising, and I will go for the label 3 decomposition. Key pap is 1. That means your you have to keep your approximation coefficients. You don't require to threshold them. Okay, and the entropy criterion, I'm choosing the Shannon entropy, and Shannon entropy doesn't require any the threshold parameter associated with it, so this is 0. And the thresholding type, I'm choosing the soft thresholding, and this is the simply signal extension mode, that is a periodic. And this is your function, okay, WP DEC, which I have already explained. So this will decompose your input signal into the wavelet packet coefficients. So in the WPT you will get the decomposition tree. So this is my noisy signal XN, this is the decomposition label, wavelet's name, entropy criterion, and the associated value. So after execution, I'm carrying this wavelet packet decomposition tree. So this tree will be utilized in denoising function. So now let me find the value of the threshold. So with these lines, I am finding the threshold using the median absolute deviation. So first I will estimate the noise variance. So I'm collecting all the wavelet packet coefficients which are detailed coefficients at label 1. Okay, and then I am finding the noise variance, that is sigma, with that median absolute deviation. I am the median of all these detailed coefficients divided by 0.6745. So this formula I have already discussed in the previous slides. And then once this sigma is known, then with this sigma value I can find the threshold value with it with that universal threshold method. So that is the square root 2 log length of the detailed coefficient. So with this formula I am now finding the threshold value. So this threshold value will be utilized in denoising. So this is the function WP den CMP for denoising. So wavelet packet tree is passed here. SO, S or H, I mean the soft or hard thresholding type is passed, and here in place of E criterion I am using the no best. No best because I want to use the full tree for denoising. I do not want any best tree, okay, on the basis of the any entropy criterion. So I'm taking or I'm considering the full decomposition tree. So that's why I have written the denoising with the full tree. So if you write the no best, then full tree will be considered. So this is the threshold value, and key pap is 1. That means your approximation coefficients will not be thresholded. So in XD I will achieve the denoised signal, and in WP tree 1 I will achieve the full decomposition tree. And in this second line of code I'm using the same function, but here I'm denoising with the best tree. So in place of the E criterion I'm writing that criterion name. So in the previous slide I have already given this criterion name as Shannon criterion. So that means for each node this will calculate the Shannon entropy, and on the basis of that entropy it will calculate the best tree. So that best tree will be denoised. Okay, so I will get that signal into the XDD, and these commands are used for plotting various signals such as the noisy signals, denoise signals with full tree, denoise with a best tree, comparison of both, and then difference of both the outputs, and then plotting these wavelet packet decomposition tree, I mean the full tree and the best tree. So let me run this program and see what type of output I will achieve. So let me jump to the MATLAB editor, and this program is already there. I have just I have to run this program. So first I will show you this denoising process with the MATLAB inbuilt noisy signals. So I'm taking this first one, that is a noise block. So let me run this program. and this is the output. So this is the bass tree, okay, which I'm getting, and this is the corresponding output, which is the denoised. And this is the full tree decomposition, and this is the corresponding denoise output. And this plot is actually showing the difference between the two outputs, the one which is obtained with the full tree and other is obtained with the bass tree. So you can see that I'm getting the slight differences only at these certain points. Okay, so this thick black line is showing the differences. All the time it is 0, but at certain points I'm getting the slight differences, particularly at this discontinuity levels. And this is overall output. You can see that this is your input noisy signal, which is corrupted by the Gaussian noise, and this is the output. So this is the output with the full tree, and this is output with the bass tree, and these two outputs are plotted together. So this is how we achieve the denoised signal using wavelet packet transform. Now let me try one more input. So let's say noise bump, another one. So I have just uncommented it and run this program. Okay, so this is the output, and it is the bass tree which is obtained using the entropy criterion, and this is the corresponding denoise output, and this is the full decomposition tree, and this is corresponding output. And here I have shown the differences of the two outputs, and here I am getting the 0 line. It means both the signals are exactly same, either you are using full tree or the bass tree. So I'm getting the 0 difference all the time. And here you can see all 4 signals. So this is your input noisy signal, this is the denoise signal with the full tree, this is the denoise signal with the bass tree, and both the denoise signals put together here for the comparison. Okay, so this is how you can achieve the denoising process with the wavelet packet transform. And now let me try this program on my own signal. So here I will give input some audio signals. Okay, so I will uncomment this section, and let me run this program. So it asked me to choose the audio stream. So first I am choosing this mp3 file. It's a 10-second flute audio. Okay, so let's see the output. Okay, so this is the bass tree which is computed, and this is the corresponding denoised output. This is the full tree decomposition tree, and this is the corresponding output. And here the difference, I mean both the signals are put together, so almost no difference is visible. And here you can see all the signals together. So this first one is the noisy signal, and the second one is the denoised output with full tree and with the bass tree. And here both the outputs are put together for comparison. So here just by looking the signal, you cannot have idea about whether my signal is denoised or not. Although I'm able to see something like at this time instant, I mean at 2, I'm getting this width of audio, but here I'm getting the lesser width of the audio. So something happened with the audio, but I cannot say how much denoising is performed. So if you can listen the noisy input and the denoise output, then you can have the better idea about the denoising. So first I'm playing the noisy signal, so just listen carefully. So this was the noisy signal, and here you could listen the lots of hissing background sound. Okay, so now let me play the denoised signal and listen carefully. So this was the denoised output, and you can see that the background hissing noise is considerably suppressed. Okay, so that is the output. And now let me show you another input. So I'm taking this WMB window media file, and let me run this program. Okay, so this is the output, and by observing this output I'm not able to see the denoising. So let me make you listen noisy signal and the denoised signal. So first we will listen the noisy signal. So listen carefully. Okay, so again you can listen the lots of hissing background noise in this case. So now let me play the denoised output. Okay, so a nice output I achieved. The hissing background is suppressed considerably. Okay, so this is what about the denoising of the one-dimensional signals. So now let me come to the denoising of the images. So here this is the program. First I am choosing my input grayscale image. So this grayscale image, after reading, goes to this variable img, and then I am adding the white Gaussian noise to this image with a 0 mean value and the variance of 0.01. So the IMGN carries the noisy image, and here are some parameters, the same parameters which I have used in 1D case. The almost same I am using here. So the Simlet 4 wavelet I am using, and the label 3 decomposition keypap. I mean I will not allow to threshold the approximation coefficients. Shannon entropy criterion is used, and the soft thresholding is utilized. And this is the function WP-2. So that is used to decompose the images in the wavelet packet coefficients, and the decomposition tree I am achieving in WPT variable. And now I have to calculate the threshold value. So first I have to collect all the detail coefficients at label 1. So I am collecting all the detail coefficients. Actually here I am collecting all the 3 matrices, so which are relevant to the horizontal detail, vertical detail, and the diagonal detail coefficients, since it is an image. Okay. And now I am calculating the noise variance sigma, again with that MAD method. So median absolute method divided by 0.6745, and then we are calculating this universal threshold or square root log method. So the sigma multiplied with the square root 2 log length of the detail coefficients. So by this way I can find the value of the threshold. Okay. And fortunately MATLAB also has an inbuilt function, wavelet threshold manager. So if you run this command, I mean this line, you will get the same output, same value of the t, which I have achieved with these 2 lines or 3 lines. Okay. If you do not want to write these 3 lines, you can use this single line to achieve the same threshold value t with the same method. And here I am reducing this threshold value by 3. Okay, so this threshold I will use for denoising. Why I am using this? If you are aware with the square root log method or MAD sigma estimation, you may know that this method, I mean this median absolute deviation method, actually the overestimates the noise variance. So in this case the estimated threshold is too large. So if you use that threshold value, you will get the over smoothing or over filtering. So just empirically I found that if you choose the t by 3, I mean 1/3 of the estimated value, your results are very good. Okay. And now I am using this WP-DNCMP function for denoising. So here I am passing this decomposition tree, soft thresholding, and first I am choosing the no best. No best means I am not choosing any best tree for filtering. So the full decomposition tree will be utilized. This is the threshold value, and the key pap, I mean your approximation coefficients will not be thresholded. And if you execute the second line, then denoising will be done with the batch tree. So here I have given the entropy criterion, that is a Shannon entropy criterion. Okay, so after the thresholding, I achieved the image in the double format. So I'm converting that into the unsigned integer for this display purpose. And here I'm calculating the PSNR between the input ground truth image, okay, GT image, ground truth image, and the denoised image. So that I can have the idea about the denoising performance. So it is a simple just calculating the MSE, I mean the mean square error, and then utilizing that formula 10 log 10 maximum square upon MSE. So that's the standard formula for finding PSNR. And once PSNR is calculated, it is printed by this formatted line, and this is all done to display the PSNR values in form of image, and then showing the original image, noisy image, and the denoise image, and the PSNR value. So let me run this program and let's see how does it perform. So first I have to jump to the editor. So this is the MATLAB editor and program is here. So I'm just running it, and it asks me to choose my image. So first I'm choosing the Lena, and okay, so this is the output. So here you can see that this is your original image and this is the noisy image. So lots of noise is added here, and this is the denoised image, and this is the corresponding PSNR. So between the original image, ground truth image, and the denoise image. So it's a quite decent value. So let me show you by zooming it, so you can have the idea about the noise. So this is your original image, and this is a noisy image. So lots of noise is added, and this is the denoised image. So it's a quite decent. So visual quality is quite okay. And let me try another image. Let's say this pepper image. So again I'm getting 27.96, almost 28 PSNR. So this is the noisy image and this is the denoise image, again the good quality. And let me try one more, this one. Okay, so this is your original image, noisy image, and the denoise image, and the corresponding PSNR is 30.4765. So again let me zoom it to visualize the quality of denoising. So this is the input original image and this is the corrupted image. So you can see that lots of noise is added, and this is the denoised output. So it's quite clean. So wavelet packet based scheme is performing well. So you can just compare. This is the ground truth image and this is the denoise image, and this is the corresponding PSNR which I am achieving with these two. So this is what we have seen in this video. So we have seen in this video that the wavelet packet based denoising is performing well for both one-dimensional signals. We have seen the audio signals by listening the quality of the denoising, and we have seen these images. So the wavelet packet scheme is working well, and one can implement these schemes with these codes which I have explained. So thank you very much for watching this video. I hope you have liked it. Please share this video to others, and definitely I will come next with some interesting videos. So thank you very much once again. Have a nice day.